Welcome to my tutorial about silent tuning and why it's waste of time. In live capture, room capture and FR capture there is an optimizer which do the equalization work much quicker. If you know the answer of why silent tuning is a waste of time and or already know how to do silent tuning, you can now jump 9 minutes forward. Let's first start with to repeat how real-time transfer function works. Later I will show how silent tuning is implemented. So here we have a block diagram over the system. We have a DSP and an amplifier and a loudspeaker, which we want to be equalized and apply maybe delay and gain adjustment with the DSP. Here we have the analyzer consisting of a PC with a sound card and software, in this case Live Capture Pro. We connect the microphones to the input. I recommend that several microphones is used, at least 3 of them, or measure in at least 3 positions. Then we need a reference from the noise generator here, and this also feed the DSP like this. And now we need to have a delay for compensating for this propagation delay, which occur between the microphone and the loudspeaker. And there need to be one delay setting for each microphone if multiple microphone is used. So these signals go into the software, and the reference, the delayed reference, is then divided. So we will have a trace here which show the transfer function of the system. The benefit of real-time transfer function is that the measurement will be in real time. So as the loudspeaker and the DSP is in the same loop, and the adjustment here in the DSP with equalization or delay will be seen in real time in the computer display. And here we have the result. We have measured in 3 different positions, and in that way we avoid to make a position dependent measurement. So reflections and so on will be different in different positions, and the idea is that we make an average over all this position, and I recommend at least 3, but maybe concert hall and so on it's necessary to have 7 or more. So here we have the average of this measurement, and then we want to equalize this. Yes, here we have the real-time measurement, and we have applied noise to the system. Accelerated sweep or sharp can also be used like this, but noise have a little bit better power density in this case. So now I have to emulate a filter, and I use in the Live Capture optimizer there is a listening tool. So here I can emulate, for example, a lake processor by pressing this button, and then you can see that I can add filters here to make the equalization. And here is the real-time transfer function, and I start to apply some filters. And as you can see, we equalize the curve. I can also apply a user weighting curve if I don't like to have the target flat, but another curve which you can design yourself or using the standard curves we have in the software. And then you can see that then you have to adjust the filters accordingly. The problem here with the real-time transfer function measurement is this noise generator. It's very annoying for the rest of the crew to have this noise maybe for an hour or more, especially if there are outfills and front fills and a lot of speakers which have to be equalized. So the solution is that to make this silent tuning, and we disconnect the microphones and the amplifier, and then we measure the DSP directly. And what we do is that we invert this trace so we can adjust the DSP filters to the inverse curve here, and then we connect the DSP to the amplifier again. Then we have the desired equalization. But there are more problems here that today very often the DSP and the amplifier is one unit, and therefore it's hard to pick this signal here. So one have to use a separate DSP or filtering external from the amplifiers. It's not a good idea to connect the amplifier via a pad to the sound card, because very often the processing here is crossover and so on, and you don't want to measure of the crossover and take those curves in consideration. Here is the saved transfer function, and transfer function can be saved by pressing this little button, and then we can make an inversion of this curve, and we have that here. So this is the curve we want to create with the filters to have a flat response. So let's start the silent noise and apply some filters. So here we go, and we can do these filters without having the noise in the loudspeaker system. So we can go on and finalize the equalization in that way. When then the filters are done here, then it's just to turn off the noise generator and unmute the amplifiers, and then the system is ready to go. Here is a faster and more robust way to tune a system. The filter will be calculated by the optimizer sequence. You don't need to dial in all parameters by hand to the equalizer. We start the sequence by checking the presets. We have a preset here called top alignment, and that gives us a log sine sweep. We can use the accelerated sharp as we don't need to calculate any acoustical parameters which require a standard log sine sweep, and in that way with the sharp we also avoid to have this steady pink noise. We apply a multi-time window of 4 milliseconds for the small window, and we don't use smoothing. I will come back in another presentation why you should never use smoothing in this case. And the stimulus sounds like this. And then we make 3 measurements. At least 3 measurements I recommend. Looks like this. And then we choose these 3 and make an average. I will also come back in another presentation about windowing and averaging. So now we have average trace over the 3 position, so we can start to use that for the equalization. Next step is to go to the target tab and adjust the level. So we define a passband like this. Here we can also apply a target curve. Come back on that. And in the optimizer we choose among hardware here. I select the Lake processor, and it have up to 27 filters. And here we can have some steering parameters, and we select the passband we want to equalize. And then we start the optimizer. And then we can read the result here. We can see the measurement and the filter, and then the result. If we look at the filters, here we have a couple of very high Q peaks, which we maybe should avoid. Here we have one, so we can actually disable these high Q peaking, because that will create some ringing and so on in the result. We can listen to the filters here. We have an emulation algorithm which you either can select a WAV file to listen to, and you can enable equalization or not to hear the difference, and you can also do some equalization in real time. But you can't use it for live music, as the latency is about 70 milliseconds through the algorithms and the computer. We can go back and avoid these peaking filters by select another maximum Q value or a minimum bandwidth. Let's do like this. And then we run the optimizer again. Like this. And then you see that we have avoided these peaks here. Then you can export this list. In this case, it will be transferred to the Lake controller software in the overlays folder. You can go back to the target here and select a target. If you don't want to have it flat, you can make a curve like this, and we adjust the level like this and go to the optimizer and start it, and here we go. We have a list of parametric filter or raised cosine parametric filters which we can export to the hardware.